In this video, we're going to talk about how we can derive the equation for half-life. So we're going to start with this equation. A is equal to PE raised to the RT. So this equation is associated with exponential growth, particularly when that growth is compounded continuously. P is the principal, A is the future value of the account, R is the interest rate or the growth rate, and T is the time. And E is a number, 2.71828, and so forth. It's the inverse of the natural log function. Now, we can replace P with A initial. We can replace A with A final, because that's the final amount. And since we're dealing with chemistry, we could replace R with the rate constant K. Now, when dealing with half-life problems, you're dealing with exponential decay as opposed to exponential growth. So we're going to have a negative sign in front of K since we're dealing with exponential decay. And we can keep T the same. So this is one equation that you want to be familiar with. Now the next thing we're going to do is we're going to take the natural log of both sides. So we're going to have ln A final is equal to ln A initial e raised to the negative kt. Now a property of logs allows us to take one log and split it into two. For instance, let's say if we have log A times B, we can expand it and write it like this: log A plus log B. In this case, we're going to separate A initial from E negative kt. So we can write it as ln A initial plus ln E raised to the negative kt. Now, another property of logs, known as the power rule, allows us to move the exponent to the front. So log A squared is the same as 2 log A. So what we're going to do here is we're going to take this exponent, negative kt, and move it to the front. So we have ln A final is equal to ln A initial minus kt ln E. Now the natural log of E is equivalent to 1. So we could simply get rid of this. Now I'm going to rewrite this equation in slope-intercept form. ln A final is equal to negative kt plus ln A initial. So this is the integrated rate law expression for a first order reaction in slope-intercept form. This is y is equal to mx plus b. So the y-intercept is ln A initial. The slope is negative k. So that's for a first order reaction. For a zero order reaction, you have a similar expression but without the natural log symbol. And for second order reaction, it looks like this. It's going to be positive kt instead of negative kt this time. But going back to this expression, we need to calculate the half-life. Now, as A initial goes to A final, some time t will elapse. The half-life is the time it takes for half the substance to decay. So that means that A initial goes down to 1/2 of what it started from. In other words, if we started with 100% of the initial substance, the half-life is the time it takes for half of it to remain. 100%, we can replace that with 1. 50%, we can make that 0.50, which is the same as 1/2. So I'm going to use these two numbers. So ln A final, I'm going to replace A final with 1/2. T, I'm going to replace it with T sub 1/2 because we're now dealing with the half-life when A initial becomes half of what it was. A initial, we're going to give it a value of 100% or 1. Now, 1/2 is the same as 2 raised to the negative 1. Here, this is 1 over 2 to the positive 1, but when you move the 2 to the top, the exponent changes sign and becomes 2 to the negative 1. Now, we said that ln E is equal to 1. You also need to know that the natural log of 1 is 0. So this disappears. Now, what we can do at this point is we could take the negative 1 and move it to the front. So we have negative ln 2 is equal to negative k times t to the 1/2. Now, if we multiply both sides by negative 1, the negative sign will disappear. And we're just going to get this. So to get the half-life, we need to divide both sides by k. Therefore, the half-life equation for a first-order reaction is this. It's equal to the natural log of 2 divided by the rate constant k. So for a first-order reaction, the half-life does not depend on the initial concentration of the substance. It only depends on the rate constant k, which means the half-life is constant because the rate is constant. K is constant. So for a first-order reaction, the half-life doesn't change. It's dependent on the rate constant k. By the way, when I say it doesn't change, I mean with respect to the initial concentration. If you change the initial concentration of the substance, the half-life is not going to change for a first-order reaction. Now, let's focus on a zero-order reaction. Let's get the half-life equation for that. So we're going to start with this expression, which corresponds to a zero-order reaction. Now, it's going to be a little bit different. First, I'm going to subtract both sides by A initial. So on the left, I'm going to have A final is equal to, it's going to be A final minus A initial, which is equal to negative KT. And then I'm going to divide both sides by negative K. So at this point, we have the change in concentration, final minus initial, over the rate constant K is equal to T. Now, in order to change T to T sub half, we need to address A initial and A final. The half-life is going to be the time it takes for A initial to become 1/2 of its value. However, for the zero order and the second order reaction, it won't work well if we replace A initial and A final with 1 and 1/2. So instead, we're going to replace A initial with we're going to replace A final with half of A initial. Because that's the half-life. The time it takes for half of this to decay, which means half is going to be left over. The reason why we need to do this for the zero order and the second order reaction is because the half-life is dependent on the initial concentration. For the first order reaction, the half-life does not depend on the initial concentration. So we could use a ratio of numbers instead of exact numbers. Here we can't do that, so we need to use this. So let's replace A final with 1/2 A initial. T now becomes T 1/2. Now 1/2 minus 1 is negative 1/2. So we're going to have negative 1/2 A initial over negative K. Now, to get rid of the negative sign, we could basically, once we divide these two negative signs, they will cancel and become positive. And to get rid of the fraction, we can multiply the top and the bottom by 2. 2 times 1/2 is 1. So this is going to simplify to A initial over 2K. So that is the half-life equation for a zero-order reaction. As you can see, the half-life for a zero-order reaction is dependent on the initial concentration. If you increase the initial concentration, the half-life is going to increase. Now, let's move on to a second-order reaction, where we have this 1 over A final is equal to positive KT plus 1 over A initial. So just like before, we're going to take this term and move it to the other side. So we're going to have 1 over A final minus 1 over A initial is equal to KT. But I'm going to divide both sides by K. So these will cancel. And this is going to equal to T. So as A initial goes to A final, sometime T will elapse. Now just like before, in order to change T to T sub 1/2, we need to replace A final with 1/2 of A initial. So this is going to be 1 over 1/2 A initial minus 1 over A initial divided by, and this time it's positive K. And now we can replace T with T 1/2. So to get rid of this fraction, I'm going to multiply the top and bottom by 2. So we're going to have 2 over, 2 times the half is 1, so this is just 2 over A initial minus 1 over A initial all over K. Two minus 1 is just 1, and we already have common denominators, so we can write it as a single fraction. So it's just going to be 1 over A initial divided by K. Next, I'm going to multiply the top and the bottom by A initial. So these will cancel, just giving us 1. And on the bottom we have A initial times K. So that is the half-life equation for a second-order reaction. Notice the difference between a second-order reaction and a zero-order reaction. The half-life expression for a zero-order reaction was A initial over 2K. And for first order reaction, half-life is equal to ln2 over K. So in all cases, the half-life is inversely related to K. So for all three rate orders, 0, first, and second order, as the rate constant increases, the half-life will decrease. You always have that inverse relationship because K is always in the bottom of the fraction. Now for first order reaction, if you were to increase the initial concentration, it will have no effect on the half-life. The half-life won't go up, nor will it go down. For a zero order reaction, because this is the numerator, the half-life is directly proportional to the initial concentration. If you increase the initial concentration, the half-life will increase in proportion, which means if you double the initial concentration, the half-life will double. If you triple the initial concentration, the half-life will triple. For a second order reaction, we see an inverse relationship. If you increase the initial concentration, the half-life will decrease. And if you decrease the initial concentration, the half-life will increase. So it's opposite. But that's basically it for this video. So now you know how to derive the formula for half-life for a zero order reaction, a first order reaction, and a second order reaction. By the way, for those of you who want practice problems on integrated rate laws, feel free to check the video description, the description section below this video when you get a chance. Also, if you want example problems on half-life questions, I'm going to put another video in the description section for that as well too. So feel free to take a look at that when you get a chance. Thanks for watching.